Hello, my name is Nurul Aim 39 and my matrix number is AA212327. For the first objective, you have to do the formula coding at the MATLAB to get the graph, and for the calculation, you have to put the equation into the closed loop formula, and then for the excess value, you have to use the quadratic formula and change it to the imaginary number to get the answer. Next is second objective. To get the graph, you have to put the circuits on the Simulink, and the components are step, subtract, transfer FCN, and scope. To get the graph, you have to click the scope and the graph will be there. And to get the information for rising time, settling time, steady state error, and overshoot, you have to add the step info T in the bracket at the coding, and you will get all of the informations. And lastly, for the third objective, to get the PID graph, you have to add PID controller at our circuit in Simulink. And to get the info, just like what I said before, we have to add step info in bracket T to get the settling time, rising time, overshoot, and steady state error. And for the info to our graph, our stable graph is PD circuit is with overshoot 1%, settling time 0.9 seconds, and for the PID graph, settling time is 1 second, overshoot is 1%, and that's all for the first circuit.
Hi, my name is Muhammad Sukri. I will present for the closed loop system number 2. So this is the calculation to determine the poles and zero. Based on the poles and zero plot, we can determine that the system is stable because of the poles is plotted at the left side plane. Next is objective number 2. So this is the step response for the system number 2. By referring to the step response, we can determine that the graph is under damped because of it has the overshoot. The overshoot value is 55.20%. The rise time is 0.22 seconds. Settling time is 3.72 seconds. The steady state error is 0. The last one is objective number 3. For P controller, it has high overshoot, which is 85.60%. For PI controller, it also has the high overshoot, which is 88.88%. And for the PD controller, it has low overshoot, which is 1.95% and 0.019 SSE value. However, for the PID controller, it has zero overshoot and also 0.003 SSE value, which is lower than the PD controller. The conclusion is PID controller is the best controller to optimize the closed loop system number 2.
Hi, my name is Nur Syaza Alia binti Hasaitan Manja. My matric number AA212340. I want to present question 3 for objective 1, which is poles and zero. For this question, the HS is 250 divided by s square plus 4s plus 50, and the GS is 1, which is unity. Next, we need to insert the fraction and unity in the formula transfer function, which is gs over 1 plus or minus hs multiplied to gs. After we get the answer, we need to equal gs equal to 0, which is for 0, and hs equal to 0 for the poles, and we get 0, no 0, and the poles is equal to -2 plus or minus 17.2047. For the objective 2, which is about the graph, overshoot, rise time, settling time, and steady state error. For my question, which is number 3, The overshoot is 69.36, rise time 0.0659, settling time 1.8667, and steady state error equal to 0. The graph is stable because the graph bigger in the left side and smaller in the right side. Next, for the objective 3, firstly, I put Kp equal to 100, Ki and Kd equal to 0, and we get the graph which is marginally stable because it from bigger to smaller but didn't have straight line. Second, I put Kp equal to 100, Ki equal to 0, and Kd equal to 500, and I get the underdamped graph which is stable but the steady state error not equal to 0. For Kp equal to 100, Ki equal to 50, and Kd equal to 100. So the graph is stable because it gets steady state error equal to 0. Plus Kp equal to 100, Ki equal to 10, and Kd equal to 30. The overshoot is 0, the state error equal to 0. That means PID controller is the best controller to optimize the closed loop system for number 3, and PD controller is the best compare in this question because has the lower steady state error value. That's all from me. Thank you.
My name is Muhammad Akamshar bin Muhammad Zamri, and now I will explain about the closed loop 4. For the objective 1, the, the graph that I get from this is like this, which the system is unstable on the right hand side because of there are two poles here, and it is marginally stable on the x-axis with a pole. When it comes to 0, it is located at the -2 of x-axis here. Next, for the closed loop number 4, objective number 2, this is the graph that I get when the time is 10 seconds. Next, when I change the time to 2 seconds, the graph that I will get is like this. There is more oscillation that start from the beginning of the graph. Next, when P is added to the closed loop, where P is 1000, the graph that I get for the closed loop is like this, and the rest time is at 0.002, the setting time is 1.95, and the overshoot is at 98.94. When Pi is added to the closed loop, where P is 1000 and I is 500, the graph that I get is like this, and for rest time is 0.002, the setting time is 2.249, and the overshoot is 98.86, and the steady state error is at 1. When PD is added to the closed loop, where P is 1000 and D is also 1000, the graph that I get is like this, and for rest time is 8.74, setting time is 1.54, and the overshoot is 0.01. Next, when PID is added to the closed loop number 4, where P is 1000, I is 500, and D is also 1000, the graph that I get when The closed loop at 10 seconds is like this, and for the result is rest time is 8.788, settling time is 1.56, the overshoot is 0, and the steady state error is 0.